So we've talked in a previous movie about how to perform calculations for heat exchange between substances. And in this video, we'll talk about the experimental method for measuring heat exchange. And that method is called calorimetry. Now the basic premise behind calorimetry is pretty straightforward. You have some sort of vessel, the calorimeter, with a thermometer inserted into the calorimeter, often inside of water, and we have a reaction that goes on inside of the calorimeter, and heat is exchanged between the reaction and the surroundings, which include the calorimeter, the thermometer, whatever solvent is around, and so forth. So heat of the reaction plus heat of the surroundings by the first law of thermodynamics must equal zero. In other words, energy is neither created or destroyed, and so whatever heat is liberated from the reaction must be absorbed from the surroundings, and vice versa. If the reaction absorbs heat, then that heat must have come from the various parts of the surrounding. And therefore we can maintain the first law of thermodynamics, in which the energy of the universe is neither created nor destroyed. Okay, so remember that in doing a calculation then for a heat of reaction inside a calorimeter, we're going to be looking at the heat exchanged to the surroundings. And from our previous video, we know that we can use a couple thermochemical equations to do such calculations. That is, heat is related to the heat capacity, say for instance of your calorimeter, times the change in temperature of the calorimeter. That could be a measure of the heat exchanged from the reaction to the surroundings. We also have Q, heat, equal to the mass of a substance times its specific heat times a change in temperature. So if the reaction is occurring in water, for instance, you could use the mass of the water, its specific heat, and its temperature change, and that heat, of course, being liberated from a reaction, would provide an idea of how much heat was given off by the reaction. If you have a positive temperature change for the surroundings, in other words, the temperature of the surroundings goes up, that must mean that the reaction gave off that heat. And in this instance, the reaction is exothermic. If, on the other hand, temperature of the surroundings decreases, you would see that the thermometer temperature goes down. That means that heat is absorbed by the surroundings into the reaction, and therefore the reaction is endothermic. The most common form of calorimetry that's performed in general chemistry labs is constant pressure calorimetry. In this type of experimental setup, the pressure of the reaction is constant, open to the atmosphere, and so our calorimeter, usually a coffee cup, is open to the atmosphere so the pressure of the reaction is always equal to the pressure of the atmosphere. Under those conditions, remember that the heat liberated is proportional to the enthalpy, or is called the enthalpy for the reaction. Now remember that the heat given off by the reaction is going to be measured by the heat of the surroundings. For constant pressure calorimetry, usually the surroundings include water, which is the solvent. So heat given off by the reaction will be absorbed by the water, or if the reaction is endothermic, the heat being absorbed by the reaction will be coming from the water, along with the calorimeter, the thermometer, and whatever else might be in the surroundings. So the reaction is proceeding. Say it is giving off heat, that heat will be absorbed by the water, the calorimeter, the thermometer, and anything else that's in the surroundings. Now usually for these types of problems though, we simplify them a little because we can't measure heat exchange to everything. We assume that the heat to many parts of the surrounding, including the thermometer and often even the calorimeter, that heat exchange to those parts of the surroundings is negligible. So even though we don't have a perfectly isolated system, we make some assumptions to get it to be a little easier to do the calculation. So now we have heat of the reaction is essentially heat going to be measured by the heat exchanged to the water. So let's do a practice calculation. Okay, so when 150 milliliters of 1.5 molar HCl and 150 milliliters of 1.5 molar NaOH, both solutions initially at 25.5 degrees Celsius, are mixed in a coffee cup calorimeter at constant pressure, the temperature of the mixture increases to 35.6 degrees Celsius. Calculate the enthalpy of this neutralization reaction. And there are a couple assumptions that go into this problem. First, and you should do this if it's not specifically noted, assume the specific heat and density of the solution, in other words the NaOH and HCl mixture, are the same as those for pure water, and that the heat absorbed by the calorimeter is negligible. Since a heat capacity was not supplied for the calorimeter in this problem, we can assume that the heat absorbed by the calorimeter is going to be considered negligible. If you are to take into account heat absorbed by the calorimeter, then the heat capacity of the calorimeter would have to be supplied. Okay, so let's make a drawing to help us out with this problem. We have a coffee cup calorimeter. We have 150 milliliters of 1.5 molar HCl. Say it's in a little graduated cylinder here. And then we also have 150 milliliters of 1.5 molar sodium hydroxide, maybe in a separate graduated cylinder. Okay, we know that the starting temperature of both solutions is 25.5 degrees Celsius. When we mix the two solutions, we'll have a total volume of 300 milliliters, and we know that after the reaction occurs, that the temperature increases to 35.6. So about 11.1 degrees Celsius. So we've mixed the two solutions, the reaction occurs, temperature of the solution goes up. So this means that the reaction is giving off heat. We're going to calculate the enthalpy for this neutralization reaction, and here's the reaction. Neutralization of HCl with NaOH to form water and sodium chloride. That's the reaction that's occurring. This is your system. This reaction is the system. The surroundings are the water and the calorimeter, the thermometer, but we're assuming that heat absorbed by the calorimeter and the thermometer is negligible, and so we're going to just use heat exchange to the water as measured by the temperature change of the water to estimate the heat given off by the reaction. So, heat of the reaction equal negative heat exchange from the water. We can calculate the heat exchange for the water from the mass of the water, its specific heat, and the change in temperature. Now, mass of water we don't know, but we do know the volume. The total volume was 300 milliliters. Once the two solutions were mixed. And the density of water is 1 gram per milliliter, and therefore our 300 milliliters should weigh 300 grams. So we can insert that into the equation. The specific heat of water is known, 4.184 joules per gram degree Celsius. And the temperature change, we know, the final temperature was 35.6, initial temperature 25.5, so that's 11.1 degrees Celsius change. Canceling units, leaves us with units of joules, which is the unit for energy, heat in this case, and we have 12,678 joules, therefore 12.7 kilojoules of heat exchanged to the water. Now, since the reaction is exothermic, Q of the reaction is equal to negative Q of the water, that means that negative 12.7 kilojoules of heat were given off by the reaction. However, we want to calculate delta H, enthalpy for the reaction, specifically for this reaction, which relates 1 mole, right, of each substance, HCl and NaOH. But the reaction was for specifically 300 grams, or I'm sorry, 150 milliliters of 1.5 molar HCl, which is not going to be exactly 1 mole of HCl. So how do we normalize this for this particular equation? Well, what we do is we calculate the actual number of moles of HCl used, and we could do this for NaOH too. It doesn't matter in this case because neither one is limiting. If there is a limiting reagent, you have to use the limiting reagent to do this portion of the calculation. So moles of HCl, let's go back again and do that. The moles of HCl in the reaction is equal to the concentration times volume, and we get 0.225 moles of HCl in this reaction. So what essentially has happened is that 12.7 kilojoules of energy were given off, so negative 12.7 kilojoules of energy from the reaction, for 0.225 moles. Per mole, then enthalpy is 12.7 kilojoules divided by the 0.225 moles of HCl actually used, and we get 56.4 kilojoules per mole for the enthalpy. And then, of course, it is negative because the reaction is exothermic.